Collision theory is a review. In order for reaction to occur, they must have the following three properties. 1. The reactants must collide. The more they collide, the better chance the reaction will occur. So we're looking for frequency. Number 2, the molecules must have fission energy. So it must meet the minimum activation energy requirement. Lastly, all collisions do not result in a reaction. The collision must be in a proper orientation for reactions to occur. Activation energy, EA, is the minimum energy needed to make a reaction happen. This is only true if there is a proper orientation. If the orientation is not proper, no reaction will occur even though the minimum energy requirement is met. In general, we use catalysts because catalyst lowers the activation energy, so the reaction will occur. The activated complex, transition state, or intermediate state, when the arrangement of molecules are at the peak of the activation energy and they are at the proper orientation for the reaction to occur. The activated complex, transition state, or intermediate state will only appear during the reaction. You will never see it as a reactant or a product in the overall reaction. Arrhenius was able to describe the temperature dependence of a rate constant. The rate constant will change when the temperature changes, so they are dependent on each other. By lowering the rate constant, the higher the activation energy. The larger the activation energy, the greater the temperature, the greater the change in the rate constant. So the Boltzmann distribution shows the number of particles with energy and displays their average. So if I look at this graph for T1, the temperature T1 is less than temperature T2. Since the temperature is less, you're going to have more number of molecules within a smaller range. If the temperature is higher, the range is going to be much larger. So example of that is if the speed limit is 30 miles per hour, pretty much everyone is going to drive at 30 miles per hour. So there are more cars within the same range. So the peak is going to be higher if we graph it. On the freeway, if the speed limit is 70 miles per hour, there's a greater range of speeds. There's going to be a lot more people driving slower, a lot more people driving a little faster, while most of the people will fall within 70 miles per hour. So if I graph the average speed, the peak will be a lot lower because the range will be a little bit greater. Same thing with molecules. When the temperature is lower, there are going to be more molecules traveling at the same speed. When the temperature is higher, the range that the molecules travel will be much greater. So this leads us to Arrhenius equation, which says K, the rate constant, is equal to A, which is the Arrhenius constant or the frequency factor, e to the negative EA, EA is the activation energy, usually in kilojoules, divided by R, which is the gas constant. But since energy is in kilojoules, we must use the gas constant in kilojoules, which is 8.315 times 10 to the negative third kilojoules per mole Kelvin. And the gas constant needs to be multiplied by the temperature, and the temperature must be in kelvins. Cancel out with the gas constant units. Here we have the decomposition of dinitrogen pentaoxide at 308 Kelvin, and it has a rate constant of 1.35 times 10 to the negative fourth. Arrhenius constant for this reaction is 4.79 times 10 to the 13th seconds to the negative first. They want you to calculate the activation energy, which is EA, for this reaction. So if you don't know where to start, identify the variables. Rate constant, we know this is going to equal to K. The Arrhenius constant, or the frequency factor, is going to be A right here. And we also know the temperature in Kelvin is equal to 308, and the gas constant R is going to be 8.31 times 10 to the negative third kilojoules per mole kelvins. So if we start with the equation above, K is equal to AE to the negative activation energy divided by the gas constant times the temperature. So to isolate the activation energy, we need to get rid of E. Opposite of E is natural log, so we have to natural log the entire equation. So this becomes ln K equals to ln A, and plus we have ln and then E, so that just cancels out here to the negative EA over RT. So if I rewrite this, this is ln K equals to ln A plus a negative EA over RT. I separated A and E. In natural logs and logs, we expand multiplication out, it becomes addition. If we have a ln A times a ln E, it is the same thing as ln A plus ln E. I need to isolate EA over RT, so I need to subtract ln A to both sides. If I subtract ln A, I subtract ln A. Ln K minus ln A, is that cancels out, equals to negative EA over RT. So next I need to distribute the negative sign. So when I do that, this becomes ln A minus ln K equals to EA over RT. To isolate EA, I need to multiply everything by RT. So on both sides. So this side I multiply by RT. On the opposite side, I multiply by RT. So EA equals to RT ln A minus ln K. So now I'm going to plug in. R is 8.31 times 10 to the negative third kilojoules per mole times Kelvin. Temperature above was 308 kelvins. Ln, so the A above, remember, was 4.79 times 10 to the 13th seconds to the first, and my K constant was right here. So I'm just going to plug that in. So that's going to equal to 4.79 times 10 to the 13th seconds to the negative first minus ln 1.35 times 10 to the negative fourth seconds to the negative first. To simplify this math, you want to do the work in the parentheses first. So the first thing you want to do is ln this number minus the natural log of this number, and afterwards you're just going to multiply all three numbers together. Punch it into the calculator correctly, you should get something like this. So my unit, the kelvins, cancel out. Next, the seconds cancel out. When you take the natural log of a number with unit, it becomes unitless. So this actually has no units after you take the natural log. So my units left over is kilojoules per mole. So it's going to be kilojoules per mole are my units. Now if we go back and do sig figs, this is a constant. It really doesn't count. The temperature, there's 3. The frequency factor has 3. And the rate constant has 3. So my final answer should have about 3. 1, 2, 3. I look one to the right. So it's 103 kilojoules per mole. Pause the video, try this one on your own, and then check your answer. So we're using the same reaction setup as above, but at a different temperature. Since the temperature is different, the rate constant has to be different. So the rate constant has a value of 2.4 times 10 to the negative third seconds to the first. So this is my K. Arrhenius constant for this reaction is 6.22 times 10 to the 13th seconds to the first. That is RA, or the frequency factor. Other conditions are the same. We're calculating the new temperature. So we're going to start with our equation. K is equal to A e to the negative EA over RT. We need to solve for temperature. So we need to do the natural log, get rid of E. So if I natural log then it's natural log k. This is equal to natural log A plus natural log E, which is negative EA over RT. So this cancels out. So I need to rearrange this by moving ln A to the opposite side because we're isolating for t. So I need to subtract ln A on both sides. So if I simplify the equation, this becomes ln k minus ln A equals to, this canceled out, minus EA over RT. So we need to isolate t. To isolate t, I need to multiply both sides by t. So I need to multiply t here and t on the opposite side because we must do the same thing. T's cancel out on the right side, and we're left with negative EA over R. Now that I have t in the numerator, I need to isolate it. I isolate it by dividing both sides by ln k minus ln A. So when I do that, this cancels out, and we have t is equal to negative activation energy divided by R times ln k minus ln A. Now I'm going to plug in. Since this is the same reaction, the activation energy has to be the same. So from above, it was equal to 103. I'm going to carry some of the digits through so temperature does not get completely truncated. This was the kilojoules per mole. The gas constant is still the same. 8.31 times 10 to the negative third kilojoules per mole Kelvin multiplied by ln. The K was given as 2.4 times 10 to the negative third seconds to the first minus ln to 6.22 times 10 to the 13 seconds to the first. So after you complete all the math, you should get approximately 329. Now let's check units. We have a kilojoules per mole on top. We have a kilojoules mole on the bottom. They cancel out. When we do natural logs, they disappear, so it's unitless. And since we have Kelvin way in the bottom, that's going to come back up. So this is going to be Kelvin. The Arrhenius equation can be written in the format of a line equation. So the equation of the line is y is equal to mx plus b. So ln k is your y-axis, the vertical axis in your graph. ln A or b is the y-intercept, and mx is your slope. So my slope here is activation energy over the gas constant, and in the horizontal axis it's 1 over temperature. So here is what a general sketch would look like. On the horizontal axis, it'll be 1 over temperature, and so the units will be kelvins to the negative first. Vertical axis, it'll be ln k, and it will be dimensionless because natural log a number, the units disappear. So my slope is EA over R. If you look here, it's a negative slope. So if I sketch this slope will be downward. And the slope of this line here will be activation energy over the gas constant. In the Arrhenius plot, ln k is the y-axis. 1 over temperature is the x-axis. So if I have data provided as temperature and the K constant or the rate constant, the first thing I need to do is for the temperature, I need to take the reciprocal because that represents the horizontal axis, x. And for the rate constant, I need to take the ln K of it, which represents the y. Plotting these points, you get the following Arrhenius plot. So the general equation was ln k is equal to ln A minus EA over R, the gas constant, times 1 over temperature. ln k is your y-axis, just like here. Your ln A is your frequency factor. Your activation energy over the gas constant is your slope, and 1 over t is your x as we plotted. To find the slope, we pick 2 points on the line and take the slope of it. I'm going to pick this point off the line right here. And when you graph, you should always circle your points. Find the slope. After you draw your best fit line, you want to pick 2 points off the line not from the data table, off the line. Slope is equal to change in ln k, which is my vertical, over my change in 1 over t, which is my horizontal. So now I'm going to plug in. This one is approximately 0.005 and negative 85 and negative 85. The other point is going to be 0.003 and negative 45. So you're going to plot these points. So the change in ln k is ln k final minus ln k initial for 1 over t final minus 1 over t initial. So this becomes negative 85 minus 45 divided by 0.005 minus 0.003. This equals, and what did we say the slope was? Activation energy over the gas constant. It came out negative because there's a negative sign, so the slope is going downward. That means EA over R is equal to, and we could actually solve for EA because we know what R is. R is 8.31 times 10 to the negative third kilojoules per mole Kelvin. So my general equation for the rate constant for Arrhenius is K is equal to the frequency factor or the Arrhenius factor, e to the negative EA over RT. To solve for A, we need to divide both sides by this. So that means A is going to equal to K, the rate constant, e to the negative EA over RT. So how do I solve for the frequency factor? By choosing a temperature and K value. So that means depending on the K you choose and the rate constants, the frequency factor will change. So choose K and A. So the Arrhenius equation obeys reaction rate data. The fraction of molecules possessing activation energy or greater, the number of collisions occurring per second, and the fraction of collisions that have appropriate orientation. So pretty much it follows the collision theory. Potential energy diagrams shows the change in potential energy of a system as reactants are converted to products. So the vertical is potential energy using kilojoules. The horizontal axis is either reaction pathway, reaction coordinate, or time. In this picture, we have reactants on the left side. Therefore, this reaction is going from left to right. In order for the reactants to be converted into product, it must have enough energy to overcome the activation energy. Once it reaches the peak of the activation energy, right here, you will have the activated complex transition state or the intermediate state. This is the point in which molecules collide with proper orientation and have met the minimal activation energy. The activated complex transition state or intermediate state is very brief. It doesn't last a very long time. We can measure all the energies of the reactants, the reaction, the products, and the activation energy through this diagram. Usually, the delta H of the reactants and products are measured from the horizontal axes. The delta H of the reaction is equal to product minus reactant. You could rewrite it as delta H reaction is equal to delta H product minus delta H reactant. When the energies come out negative, then it is exothermic. That means the product have lower enthalpy than the reactants. If the reaction comes out positive, it's an endothermic reaction. and the product's enthalpy is higher than the reactant. The activation energy is always measured from the reactant to the top of the energy hill or the peak of the hill where the activated complex is located. If this reaction is a forward reaction, then the reactants are on the left side and the products are on the right side. If it's a reverse reaction, then the products now become reactants and the reactants now become products. So that means starting this unit, a lot of the equations are going to be reversible. So in general, these are the simplest of the potential energy diagram. There are two types, exothermic and endothermic. Exothermic is negative delta H, endothermic is positive delta H. And if you notice, the graphs are very similar. The main difference is if I look at my exothermic, my reactants are always higher than my products. So that means my reactants have a higher enthalpy than my product. In endothermic, my product have a higher enthalpy than my reactants. In addition, the activation energy is always from the reactants to the top of the peak. However, if you notice endothermic, the activation energy is a lot higher than exothermic. This is why most reactions are exothermic rather than endothermic. This is also a potential energy diagram. The only difference is this is a little bit more complex because there is multiple steps or multiple elementary steps. Instead of having one activation energy, there's multiple activation energy. The rate limiting or rate determining transition state is the one with the highest activation energy. So in this case, it is the first hump or the first large peak. And then the second one has a lower activation energy, so it is non-limiting. The reaction can only go as fast as the limiting factor. If it needs a higher activation energy, that means it's going to be harder to get there if the available energy is not present. Note, multiple transition states require multiple humps, or you could call them bumps if you want. Catalyst increases the rate of the reaction by decreasing the activation energy by providing an alternative pathway. So what happens is the mechanism is chain. The graph is very similar. You know the uncatalyzed will have a high peak, which is right here, and this is my activation energy for the uncatalyzed, because this is my reactants and these are my product. But when I insert a catalyst, what happens to my activation energy? It lowers. And so what it does is it provides an alternative pathway. There's multiple bumps if there's more than one transition state. In this particular picture, there are two bumps, so that means there's two transition states. The rate determining transition state is this first one because it has the highest bump. If I drew the picture like this for the catalyst, then the second one here would be the rate determining step because it requires a higher activation energy. Pause the video, try these questions on your own, and then check your answer. So number one, idea of the green letters. A is the activation energy for the forward reaction. B is the delta H or the enthalpy of the reactant because it's from the horizontal axis to the reactants, A plus B. D is my enthalpy for my product. Again, it's from the horizontal axis up. And then C is my delta H or the enthalpy of the reaction, which is the product minus the reactant. Number two, is it an exo or endo? This is an exothermic reaction, and we know it's an exothermic reaction because the C plus D, which are the products, have a lower enthalpy than A plus B, which are the reactants. 3. How does the diagram change if the reaction is reversed? Then C plus D becomes your reactant. D's become my reactants. If that is true, then D becomes my delta H of the reactants. A plus B becomes my product, and my delta B now becomes the delta H of the product. C is still my delta H of the reaction, but what happens is now it is an endothermic reaction because the products A plus B is much higher than C plus D, which are the reactant. A has no effect in the reverse direction. However, my activation energy is from my reactants to B equals C. So this is my EA in my reverse direction. My green one, A, is in the forward direction. What is B equals to C called? That is the activated complex, transition state, or intermediate state. Is the forward or the reverse favored? The forward is going to be favored. Why? It has less activation energy. So if I look at my picture here, this is the activation energy for the forward. This is my activation energy for the reverse. Forward reaction will be favored. So if I draw a catalyst, it just has to be lower than what is given. So this is my catalyst labeled, and it provides an alternative pathway for the reaction to occur. Pause the video, try this problem on your own, and then check your answer. Number 1, it says label all parts of the graph. In the vertical axis, this will be labeled as potential energy, usually in kilojoules. In the horizontal axis, it will be reaction pathway, reaction coordinate, or time. For the forward reaction, my left will be my reactants, so my enthalpy of the reaction. So my enthalpy of the reaction will be from the horizontal axis to the reactant. That's my delta H, a reactant. On the right side of my picture will be my product. So from the horizontal to my products is my delta H for my product. From the reactants to the products, this is my delta H of the reaction. So from the reactant to the top of the hill is my activation energy in the forward direction. So if I'm going in the forward direction, I know this is going to be an exothermic reaction because my products are lower than my reactant. You can also double check by putting numbers in. The products have a lower enthalpy than the reactants. Delta H reaction is products minus reactants, so it will come out negative. If it was going in the reverse direction, left side would be my product. My delta H reactant will not be delta H products. On the right side, my products will be my reactant. And so my delta H products will not be delta H reactants. My delta H of the reaction will still be the same. However, since the products are higher, when you plug in the numbers products minus reactants, it will come out positive, so it will become an endothermic reaction. The activation energy is now right here, EA. My right side are my reactants, and activation energy is always measured from the reactants to the top of the hill. So this is going to be my reverse. In the middle right here, this will always still be the activated complex, the intermediate state, or transition state. Number 3, we are drawing a catalyst with 3 intermediate states. Since there's 3 intermediate states, we know there are 3 bumps or 3 humps. And it asks us to label the second intermediate as the rate determining step. So if I draw this, it should look something like this. The rate determining step will have the highest activation energy. So intermediate, this will be intermediate 1, 2, and 3. 1 and 3 just has to be lower than 2. 1 can be higher than 3. Or 3 can be higher than 1 in activation energy, but 1 and 3 cannot be higher than 2 if 2 is the rate determining step. So here is the rate determining. 1 and 3 are non-rate determining. In order for reactions to occur, molecules must collide, but all collisions do not result in a reaction. In order for reactions to occur, you must have proper orientation and meet the activation energy. Catalysts provide an alternative pathway for the reaction to occur by lowering the activation energy. Catalysts are never used up. They start at the reactants and they will be at the products unaltered but disappear in the overall reaction.